The last operation that we're going to look at with our del operator is the Laplacian of a scalar. The Laplacian of a scalar field V is defined as the divergence of the gradient of V. So our Laplacian V is equal to the divergence of the gradient of V. And so instead of writing that out each time, oftentimes we'll just sort of shorthand that. We'll have del squared times V. So what we can do is, of course, use our previous definitions for gradient and divergence, and from that we can get expressions in each of our three coordinate systems for our Laplacian operation. So let's start with our Cartesian coordinates. So for Cartesian, we have the Laplacian of V is equal to the second derivative of V, the second partial derivative of V with respect to x, plus the second partial derivative of V with respect to y, plus the second partial derivative of V with respect to z. And so relatively simple for our Cartesian. So now let's look at our cylindrical. Again, we're just using our previous definitions for gradient and divergence. So here the Laplacian of V is equal to, so we have 1 over rho times the partial with respect to rho of rho times the partial of V with respect to rho. So again, this is one of those cases we would want to make sure we multiply, we'd want to do this partial derivative, multiply by rho, then do this partial derivative. So be very careful about sort of the order of operations that you're doing. So our next term we have plus 1 over rho squared times the second partial derivative of V with respect to phi twice, plus the second partial derivative of V with respect to z twice. So that is our expression for the Laplacian in cylindrical coordinates. So then finally for our spherical coordinates, we have that the Laplacian, so del squared V, is equal to 1 over r squared times the partial with respect to r of r squared times the partial of V with respect to r, plus 1 divided by r squared sine of theta, partial with respect to theta of sine theta times partial V with respect to theta. So with both of these r and theta terms, again, we want to be sure to do these partial derivatives first, multiply by these terms, and then do the second partial derivatives there. So once again, just be careful with your order of operations. So then finally, we have for our last term 1 over r squared sine squared of theta times the second partial derivative of V with respect to phi twice. And so that is the expression for our Laplacian in spherical coordinates. So, of course, note that our result is a scalar field in all three of these cases. So result is a scalar field. So we've kind of looked at all possible scenarios. So with our gradient, we went from a scalar to a vector field. With our divergence, we went from a vector field to a scalar field. With our curl, we went from a vector field to a vector field. And now finally, with our Laplacian, we're going from a scalar field to a scalar field. One other thing about our terminology is that if we have our Laplacian of V is equal to 0, then we say that V is harmonic. And so we're not going to work through any examples with the Laplacian. It's pretty straightforward, just kind of a matter of being careful as you're doing those calculations. But if you do want to get some practice with that, you can see the example and skill assessment on page 91 in the textbook.